Hi all, I am Dr. K. Anita with Electronic Devices and Circuit topic. Today's topic is BJT configuration, bipolar junction transistor configuration. As we have discussed in the previous video, BJT has three configurations: common base configuration, common emitter configuration, and common collector configuration. So the first one I will be discussing is common base configuration. So we have input and output two characteristics for BJT. So in common base configuration, the base terminal is made common to both the input and the output. So the base terminal is made common. Input side, as we can see, is between the emitter and the base. So if we see with the help of the figure, so this is the common base. So this is the base terminal, this is the emitter terminal, and this is the collector terminal. So we can see that the base is made common to between the input and the output. So input is given over here and output is observed across here. So in input side is between emitter and base, output side is between collector and base, as is shown here. This is the circuit diagram showing the common base configuration of BJT. Here we have taken NPN transistor. The arrow is showing the NPN transistor, NPN, emitter, base and collector. Emitter, base and collector. So emitter base junction, EB junction should be forward biased. We are in the active region. So in order to forward bias this, the NPN N terminal of the emitter should be connected to the N terminal of the battery. So this is the power supply which is used for biasing. So the N terminal is connected to N, leading to forward bias in the input side. Similarly, we can observe at the output side, that is N is connected to the P, which is going to reverse bias. Hence we are in the active region of operation. So in order to measure the current, since we want to draw the characteristics, here for example I am obtaining the input characteristics for CB of the transistor, common base. So in order to do this, we have to measure the voltage and the current. Characteristics is nothing but obtaining the behavior of the transistor. So in the x-axis we are taking the voltage, and the y-axis we take the current. In order to obtain that, we have to have the voltmeter connected at the input side. So VBE will give the voltage at the input side, and IE, that is the emitter current, is measured with the help of an ammeter connected at the input side. We obtain the characteristics for input by keeping the output voltage constant for a transistor, that is BJT. So here we show that there is a voltmeter, there is an ammeter. By varying this power supply, we can set the VEB and note down the ammeter for different values of VCE. VCB. For different values of VCB, we obtain the characteristics for input, that is for BJT common base. So this is the circuit diagram in order to accomplish this. So this is the circuit diagram in simple by using the symbol. So here we can observe that VBE, which is forward biasing, and this is reverse biasing. So for PNP, similarly, the previous diagram was for NPN transistor. Here we are showing for PNP transistor. Only the transistor biasing is changed, that is the power supply polarities will be changing. So here we can observe that this is PNP, hence P has to be connected to P, leading to forward bias of the emitter terminal, leading and reverse bias of the collector terminal, leading to active region operation. So coming to the input and output characteristics, as I said, for different values of the output voltage, over here the output voltage what we have in the common base is VCB. So by keeping the VCB constant, we obtain the values for VEB and IE. So this is going to give us the characteristics for common base. So here we observe that x-axis we have, this is the input characteristics, x-axis we have VCB, VBE and y-axis we have IE for different values of the output voltages. For example, we have made the output voltages, we have fixed the output voltage VCB as 1, suppose we are fixed it to 2 volts. By obtaining this, we vary the output input voltage VEB in steps of zero point 0.1, because we observe, as we observe, if we see the particular circuit diagram, we observe that because this is reverse bias, if we ignore this, we have nothing but a PN junction diode forward bias. This is nothing but a PN junction diode forward bias. So over here you observe that there is N, there is P. So this is N, this is P positive. So giving to the forward bias condition, PN junction diode under forward bias. If we recollect the PN junction diode concept, forward bias PN junction diode characteristics is, so this is the characteristics, exponential characteristics, forward bias voltage, forward bias current if we observe, which says that for silicon diode 0.7 volts or 0.6 volts, the conduction starts. Hence, we have to vary this particular VEB in steps of 0.1. As I discussed, the value of the VEB will be varied in steps of 0.1. So, as we come nearer to the 0.7 volts, or we can, some books find 0.6 volts as well, the conduction of the current starts. The conduction of the current starts, and it goes on increasing exponentially, Similarly, now for different values, this will give one value of VCB gives one curve. Now we will go back to the power supply and vary the value of the VCB. By varying this VCC, we will vary the value of the VCB. Suppose this is VCB1, and similarly we will do VCB2. So for the other value of the VCB, we will obtain the value of VEB and IE, and if we plot, we will get the characteristics curve as we have shown here. Similarly, as many number of curves as required, you can obtain this. So the point to be noted over here is, for example, if we see VCB1 and VCB2 and VCB3, so VCB3 is greater than VCB2, it is greater than VCB1. For example, if I give 10 volts, so this curve corresponds to 10 volts, this is 5 volts, this is 2 volts, for example. So this is due to the phenomenon called as early effect. This is due to the phenomenon called as early effect, or which is also called as base width modulation. Base width modulation. So now what is this base width modulation? As we come across this, so we know that the output side, that is the CB junction, is reverse biased. CB junction is reverse biased. So this is nothing but, suppose we have reverse bias the PN junction diode. So P and N. When we reverse bias the PN junction diode, what happens? The depletion width increases. The depletion width increases. And we know that this is base which is lightly doped, and this is collector which is compared to base heavily doped. The depletion width extends more into the lightly doped base. So the depletion width increases more into the base as compared to the collector. So when the depletion width increases more into the base, for example, this was the base width initially. Now the depletion width increases because of the reverse bias to these two terminals. So this is the depletion width. Now it increases more into the base. So as compared to the collector, it increases more into the base. The width of the base reduces. The result of this is the reverse bias is going to extend the depletion layer into the base. Hence, the width of the base reduces. So, this is nothing but modulation of the base width depending upon the reverse bias at the CB junction. Therefore, the width of the base reduces, which is called as modulation. Hence, it is called as base width modulation. This is going to bring the curve nearer. This is going to bring cause the emitter current to increase prior to the voltage. So this is the characteristics of the input for the common base BJT. Similarly, if we obtain the output characteristics for the common base, we can observe here that output current is IC and output voltage is VCB. See the terminals over here, this is collector and this is base. Hence, output characteristics is between the output voltage, which is VCB, and output current, which is IC. So you can observe in this characteristics, this is VCB in the x-axis and IC in the y-axis. So for different values of input characteristic, for input current, for example, this is BJT is a current controlled device. Hence, by keeping the input current constant, we will obtain the output characteristics, that is, we will vary the VCB and obtain the IC variations for different values of input current, that is IE. Over here the input current is IE. Why? Because the BJT is a current controlled device. Okay, so as we observe the characteristics, we have for different values of this is different values of IE. For one value of IE, we can observe. So this is going to give you the constant current, the constant value. Why? Because we observe that what is y-axis? Y-axis is IC. So what is the value of the input current? The input current is nothing but IE. And we have learnt that IC is approximately equal to IE. Why? Because the base current is very, very negligible, that is in terms of microamps or nanoamps. Hence, we have IC is approximately equal to IE. Therefore, the characteristics is we have constant characteristics, that is for various values of IE, the value of IC is almost same. Why? Because obeying this IC is equal to IE, we have the characteristics. In this characteristics, the active region is at the center of the characteristics. So this is the active region, we can say. And over here we have the cutoff region. This region is called as cutoff region, and over here near the x-axis we have the saturation region. Almost all applications, linear applications, we find in the active region. So this is the region of operation for our BJT in the common base configuration. Very important. So in the common base configuration, we can see that if we see the current gain. So what is the current gain? Current gain is nothing but the ratio of output current to the input current. Over here, what is the output current? If we observe, output current is IC and the input current is IE. So current gain is depicted for common base by alpha. Notation is by alpha. So alpha is equal to output current, which is IC, and input current, which is IE. So current gain is equal to IC by IE. And just now we have seen that IC is approximately equal to IE. Therefore we have both almost getting cancelled. In fact, IC is a little bit smaller than IE. Therefore this is always less than 1. The current gain alpha for common base is always less than 1. So we observe that the value is 0.95 to 0.98. So the current gain is very poor in the common base configuration, hence it is rarely used. Coming to the next configuration, we have common emitter configuration for bipolar junction transistor. As the name itself says, common emitter is made common to input and output. So input is base emitter. If we see the diagram, if we see the symbol, so over here we have emitter. So emitter is made common. So emitter will be made common, and this is input side and this is output side. So this is the base. So BE junction is input side and CE junction is output side. For it to work under the active region, we have to give BE CE junction forward biasing and the CE junction reverse biasing. So input side is base emitter and output side is collector emitter. So this is the common emitter configuration we have. So here we can obtain, like in CB, input characteristics and output characteristics. So first let us see the input characteristics. So this is a plot. At the input side we have the current, which is the base current, that is IB. Input current is base current and input voltage is base emitter voltage VBE. Hence the characteristics curve is between the IB, that is the base current, and VBE. So the plot of IB versus VBE for different values of output voltage, which is VCE, we will obtain the input characteristics. As we have seen that this is nothing but, for example, this is NPN. So this is reverse biased. If we focus on this, this is nothing but PN junction diode forward bias. Hence the curve for the input characteristics is nothing but it is PN junction diode forward bias characteristics, which is nothing but this. So at 0.6 volts you are going to get the current conduction. As VB is increased, the current starts to increase, and after 0.6 volts it starts to increase exponentially. So we have a diode like curve. Now IB increases rapidly after 0.7 volts or 0.6 volts. Hence we have the characteristics similar to exponential as shown over here. So this is the input characteristics. So for different values of the output voltage, that is VCE, for different values of output voltage we are going to get the characteristics. For example, this is emitter and over here we will apply the voltmeter VCE, positive, negative, NPN. So reverse biasing, this gives us VCC and this is VCE for different values of IB. This is a particular microammeter. This is going to measure IB. So this is going to forward bias. So this is the circuit diagram which is used in order to obtain the input characteristics of BJT under CE configuration. We will use this particular VCC in order to vary the VCE and note down IC. In order to note down the IC, we will use an ammeter over here. So this is for example an IB, and over here we will be using VBE. So this particular voltmeter is going to measure the input voltage, and over here this is IB. So in order to obtain the input characteristics, so for various values of VBE, we will note down the IB for VCE values. So this is by varying this VCC, you will set the value of VCE. For example, VC is set at 2 volts. Then coming back to this is suppose VBB. By varying this power supply, set the VBE and note down IB values. Set the VBE, for example, VBE will be in terms of 0. From 0, if I start 0, 0.6, 0.65, 0.7, 0.72, 0.8. Likewise, it will be in steps of 0. You will be noting down the IB, which is in terms of microamps. So 0, for example, 0. After 0, here you have some readings. Here you will get 0, 0. And over here the current starts to increase. For example, 8 microamps, 20, 50, 100, 200. Likewise, microamps current will be flowing, which will lead to the characteristics. So this is the characteristics for one value of VCE. If I change the VCE value from 2 volts to 5 volts, I will get another curve, that is another value of VCE, which is VCE2. Similarly, we can obtain the characteristics curve which resembles the same characteristics as PN junction diode for various values of VCE. So this is the input characteristics. So with the help of these characteristics, we can as well discuss the resistances. Take one point over here, the voltage correspondingly divided by the current will give you the resistance. Coming to the output characteristics, so let us know the current and the output side. So current at the output side for common emitter is IC, current is the IC and the voltage is VCE. For various values of IB we obtain this. So the plot is nothing but between the IC and the VCE at constant input current, that is IB, because BJT is a current control device. So we have different regions of operation, cutoff, saturation and active in the output characteristics. So we know that the output current is equal to the current gain into IB. So beta is the current gain for common emitter. So we also know that IE is equal to IB plus IC. The value of beta, if we see output current by input current is IC and input current is IB. We know that IC is milliamps and IB is microamps, leading to you have some value into 10 power 6. So leading to high value of beta. So the value of beta is 20, 200, 250 likewise, which is depicting that the current gain is very high in common emitter configuration. Therefore, common emitter configuration is used in all the applications. The features which are important for common emitter configuration, we have high current gain as we discussed, that is beta. It is also called as HFV, we'll see. So it has moderate input. Any electronic circuits require high input resistance. So it has comparatively good input resistance and it has low output resistance. It is widely used as amplifier, oscillator. Coming to the characteristics, how it looks. As I said, we have the characteristics between VBE in the x-axis and IB in the y-axis. For various value of VB is always less than 1. So vary the VB in steps of 0.1 volts and note down the value of IB, which is microamps. When I do this, it is nothing but a PN junction diode for different values of VCE. So VCE 2 volts, VCE 5 volts or 6 volts, you can say VCE 10 volts. If I obtain the characteristics curve between IB and VBE, I am going to get this characteristics. So this is the input characteristics for CE configuration of BJT. Coming to the output characteristics, it is the characteristics with IC output current in the y-axis, which is milliamps, and the voltage, which is VC in the x-axis. Initially, we will vary the VC in steps of 1 or 2 volts, as you can see. The current will slowly increase initially for it to get saturated, and we know that because we know that it is IC is equal to IE, hence we have the constant characteristics for output, that is as shown in the figure. So for various values of input, different values of input, we are going to get the output characteristics. In this output characteristics, I can always show the 3 regions of operation. So this region is called as cutoff region and this region is called as saturation region, and over here, that is center of the characteristics, this region is called as active region. So active region of operation. What happens if I go over and above this? So if I go beyond this, the characteristics will go something like this. So which is nothing but breakdown region. We should never go into the breakdown region. This will lead to the breakdown of the transistor or damage of the transistor. So this is the output characteristics and input characteristics what we have learnt from the BJT configurations. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.